Good afternoon. Today, let me take you through what is food adulteration and how do we detect food adulterants, both at the household level as well as using sophisticated techniques. So, what is food adulteration or food fraud? It the definition is that it is a collective term used to describe deliberate and intentional substitution, addition, tampering, or misrepresentation of food ingredients, or food packaging. So, this includes adding something without the knowledge of the consumer, removing something, that is, for example, you can remove fat from milk, or tampering with the um, food packages, or even misrepresentation. And the economic motivation behind food fraud is different from food safety issues, food defense, and food quality. The food safety issues, food defense, and food quality generally come from unintentional addition of the product. What we discussed, some pesticide residues, could be heavy metals which come with the water where the agricultural crop is grown, or even the water that is used in the processing. So, uh, all this, what we talk about, that is the that is the intentional substitution, addition, or tampering, or misrepresenting food, all come under the umbrella of food protection, which includes food fraud, food quality, food safety, and food defense. So today mainly we will talk about food fraud or food adulteration. So, what is economically motivated adulteration? I'm sure all of you, from the title itself, I need not explain this to you. What it indicates is that you do something fraudulently so that you gain. There is some profit for you. There is some economic motivation. That means you will be getting more, or the profit will be more. It might increase the profit, or it might decrease the cost of production. In both ways, the manufacturer is the profiteer. So this includes dilution of products, very rampant in our country, diluting of milk with water. At least if it is diluted with quality water, or drinking water or packaged water, that is fine. But if they adulterate it with pond water or some other water, then that becomes a food safety or issue, or a food hazard. And if in some cases, as I said, you can remove a, a component, for example, the fat in the milk, and removing components can also be a health risk, because a consumer will read the label and assume that he is drinking milk which has 3.5% fat, but the fat has been removed and you get only 2% fat. And then, to mask this dilution, if you have removed fat, you add another fat such as an animal fat like lard, and that is even more a health hazard to the consumer. So, FSSAI in the Act defines adulterant, and adulterant is defined as, it means any material which is or could be employed for making the food unsafe, or substandard, or misbranded, or containing extraneous matter. So you see, it encompasses everything that the previous two slides said, but in a nice and compact way. So it makes it unsafe. That means you're adding something to make it unsafe. You have removed something that is substandard. You have misrepresented, which is misbranded. And if by chance there are stones, a lot of chaff material and thing, that is extraneous matter. So a product is considered adulterated if it bears or contains any poisonous or deleterious substance which may render it injurious or injurious to health. So this could mean, with reference to our country, the presence of argemone seeds in mustard seeds or argemone oil in mustard oil, the presence of kesari dal in the chana dal or in the besan powder. Second, it bears or contains any added poisonous or deleterious substance. This also is almost the same. And another example of this is nicotine, okay, which is there, which is added, like chewing tobacco. Then, if there is any filthy, putrid, or decomposed or otherwise unfit food, and this comes mainly during handling. If the product has parts of a diseased animal or an animal which has died, other than by slaughter, which I'm sure all of you had read in the newspaper. Almost a year back, we had this dead meat being sold, I think it was Kolkata. Any valuable constituent has been in whole or in part omitted or abstracted. Very good examples are where all the essential oils and the bioactives are actually extracted from spices like the cloves and the cinnamon or almonds. You see, the valuable almond oil or the spice oleoresins are extracted, and it is usually the spent spice which is sold in the market. And if any of you have had the chance to taste original clove from a tree or grower, you will find that just a single clove can actually literally burn your tongue. But what you buy in the market, you find, is mostly the spent clove. So the essential oils are removed and sold for a higher price. Damage or inferiority has been concealed in any manner. That is, for example, if you look at the turmeric powder or the chili powders, they use low quality chilies or turmeric, the turmeric tubes. So therefore, the color of the product is not um, appealing. So they adulterate the turmeric with lead chromate. They adulterate the chili powder with Sudan dye. So this is like concealing the damage or the inferiority, including, green peas having the green color, capsicum and brinjal being colored. All this is there. So any substance which has been added or mixed to increase its bulk or weight, add or reduce its quality of strength, etc. So this is, for example, you see a large number of stones in the rice. And if it bears or contains a color additive, which is unsafe with the meaning of this section. So if you see, they add many a times in the Indian market, you will find the dal, the tur dal, which is colored with methanol yellow to make it look more appealing. Or in the markets, if you see, cut pineapple slices have got methanol yellow to make it look ripe. So these are adding color additives, and especially these colors which are not permitted and which are unsafe. So who does this and why? Generally, it's the merchants and traders to make quick profit. It is because of shortage and increasing prices, consumer demands, lack of awareness among us, indifference and lethargy among consumers, because you're not bothered. As long as the price is lower, it's the. It also results if we do not have the proper enforcement of the food laws. In all respects, the food adulterated is dangerous as it is hazardous to our health. It could be toxic, and also we could be deprived of the essential nutrients. So there are two types of adulteration. One is intentional, that is added deliberately to increase the margin of profit. And the other is the incidental intentional adulteration. That means adulteration which comes in because of negligence or because of ignorance or of the HACCP or good manufacturing practices, or having good hygienic practices in the premises. This could include the larvae of insects in food, the droppings of indents, and this pesticide residues are there, because these are not added intentionally. So today, actually, we will cover mainly the intentional adulteration, that is adulteration which is economically motivated. So economically motivated adulteration, globally, these are the 10 products at the risk of food fraud. That is because they cost so much, their price is very high. Olive oil stands on top of the list, followed by fish, milk, spices, grain, honey, coffee and tea, wine, and fruit juices. So if you look at the Indian scenario of the adulteration, we have the intentional and the accidental. In the intentional adulteration, we know and we have heard of melamine in milk, increasing the nitrogen content of milk by adding melamine. This is something that is there in the melamine plates that you use. Since we measure protein by estimating nitrogen, so melamine will increase the nitrogen. And so when you multiply this by the conversion factor, the protein content will be high. Adding sugar to honey or making a fraudulent honey, adding water to milk, adding colored dyes to spice powders, masalas, the sweetmeats, lead chromate to turmeric powder, papaya seeds in black pepper, maize tendrils in saffron, adding hydrogenated fats such as vanaspati or animal fat to butter and ghee, tamarind seed powder in coffee powder, spent tea leaves, addition of cheaper meat. Argemone sometimes is intentional, but very often it is known that the argemone plant actually grows along with the mustard, and so during harvest of mustard you get argemone. Tea leaves can come into, iron filings can come into tea leaves if the equipment where the tea is manufactured is not maintained. So by wear and tear, iron filings get into the tea leaves. Nickel in vanaspati is because vanaspati is made by hydrogenation over nickel, it can accidentally get contaminated with nickel. But what is important here is, irrespective of whether it is intentional or an accidental adulteration, both are health hazards. And some of them are really severe health hazards. So adulteration of common foods, this list has been taken mainly from data from referral laboratories and etc. It could be, there could be many more, but the common ones you see: milk and milk products, dilution with water, addition of starch to make it look thicker so that the lactometer reading goes up, addition of sodium bicarbonate, addition of urea to increase the nitrogen, addition of ammonia, ammonium salts, sulfate, sucrose, glucose, all these are added to milk and milk products. You'll be wondering where cellulose is used. You will see that the channa and the not paneer, the koa, they add blotting paper into it. That is the cellulose. So they adulterate it with blotting paper. In cereal and cereal products, generally foreign matter and insect infestation. In edible oils, it can be adulterated with argemone oil, castor oil, and mineral oil. Sometimes you also find lubricating or engine oil in it. In pulses, the synthetic color methanol yellow, and then you have the kesari dal, which is used, which is much cheaper than the tur dal or pigeon pea, and it is used to adulterate pulses. Spices using unpermitted colors and mineral oil to give them the shine. Then you also have methanol yellow to dal, synthetic milk to milk, vegetable fat or oil to milk, melamine to milk, mineral oil on spices, okay, stones to cereal grains. Very recently, last year, we have heard of black paint to pepper. We have also heard about cut broom, these broom flowers being cut in the size of cumin and being added to cumin. Coloring the maize strandles with glycerine and the color tartrazine to adulterate the saffron. Tamarind seed powder and sawdust in coffee powder. Sawdust, grass, and dung powder in dhania, that is the coriander powder. Adding sugar syrup, corn syrup, fructose, glucose, high fructose corn syrup, and now rice syrup to honey. Color additives and leaves of other plants to tea leaves. Lead chromate in turmeric, mineral oil to cooking oil. And so this is what was recently projected. These two, this coloring of the black pepper with paint and using this broom, cut pieces of this to adulterate cumin. More recently, there was was a video circulating of how they make the red color of strawberries. You know, they put it into a rotator, the drum rotator, so that it gets uniformly colored. So most of these people who do these adulteration are quite innovative because they use innovative technologies to actually adulterate the food. Okay, so this is again a list that I have picked up and made. Unpermitted colors such as rhodamine, orange 2, methanol yellow, malachite green, quinoline yellow, and auramine in Indian sweets. Lard and tallow we talked about. Adding cellulose or blotting paper to chana and koya. Using artificial sweeteners in place of burger. You must, in place of sugar. You must have heard of the famous horse meat instead of beef in the burger in the UK. Adding and the lower cost juices and lower product juices to orange juice. Adding sugar to mask the taste of pomegranate juice. Sudan red dyes in chili powder and pickle. Diethylene glycol in wine. Coloring of vegetables with malachite green and capsicum also. Peas and capsicum have been colored. Then using mineral oil on fruits and vegetables to shine. Coating low-grade tur dal and coloring spent tea leaves. That means tea leaves which have already been used for making tea. Instead of throwing them away, it is colored and resold in the market. So these are all ways in which food is adulterated. So there are some simple ways to detect coloring adulterants. And if you go to the website of FSSAI, there are 2 volumes on simple tests used to detect adulterants. And very recently, FSSAI has made what is called as the Pink Book, or it is called DART. So this is the book DART, which housewives or the common consumers can use tests to detect the adulteration. They need not come to a laboratory to detect the adulterated food. So let us see what are the ways, simple ways of detecting adulterants. So maternal yellow, this is a yellow color, and this can easily be detected by adding dilute hydrochloric acid. So maternal yellow is like what you use is an indicator, like what you use for titrimetry, that it has a different color at different pH. So when acid is added to maternal yellow, it turns pink or red, more towards a violet, pink or red, depending on the concentration of maternal yellow. So a very simple test by using dilute hydrochloric acid. Similarly, if auramine is added, auramine in acid pH is colorless. So if you add hydrochloric acid to any product that has been colored with auramine, you will see there is decolorization, indicating that it is auramine. So here again, the principle is based on the acid base indicator. And then a very abundant adulterant is using aluminium foil instead of silver on sweets. You know, in most of our kaju barfi or the badam barfi and all the sweets that are made, they are actually covered earlier, were covered with silver. And this gave the aesthetic appearance, and it was used to avoid stickiness while piling the sweets. And also it is known, you know, silver is known to be an antimicrobial agent, and so therefore it was used to enhance the shelf life of the product. However, silver or silver foil is very expensive, and so instead of using silver foil, you use aluminium foil. So how do you detect aluminium foil? If you add 1 or 2 milliliters of hydrochloric acid, the aluminium will dissolve. Another way is to scrape the foil off the sweet and burn it. Silver foil burns on ignition, leaving a white spherical ball or a residue, whereas aluminium foil is reduced to a black gray ash. So in this way, you can detect the presence of aluminium in the sweets. So water in milk, very simple. It is a density test. If you have a lactometer, you can use the lactometer to check the density of the milk. Otherwise, if you take a glass slide and you add a drop of milk on the polished surface of the glass side, adulterated milk will just flow down immediately, leaving a white trail, whereas the milk, pure milk, will take a much longer time to slide down the glass slide. Starch in milk, very easy to detect. You can buy tincture iodine and add a drop of tincture iodine to the milk. If it turns blue, the milk contains starch. Starch has been added. You could also add a few drops of iodized salt. If the iodine content is high and the milk turns blue, then you know that starch has been added. For the addition of glucose into it, you can take a teaspoon of milk, and the diastick which is used to test for urine sugar is there. You can buy them and you can see the color change from blue to green indicates that glucose has been added to the milk. That is an enzyme reaction. Next is urea to milk. So in this test, you take half a teaspoon of soya flour or arhar flour and shake it along with the milk, and then take a piece of red litmus paper and expose it. If it turns blue, urea is produced. The principle of this reaction is the soya flour contains an enzyme urease, and urease breaks down urea into ammonia. Ammonia is an alkaline gas, and so alkalis will turn red litmus paper blue. So uh, in this test, your soya flour has to be fresh. A second method by which you can do is you can take 5 milliliters of milk and add 2 drops of bromothymol blue, that is the indicator that we use in titration, and the blue color will indicate the presence of urea. It takes a longer time. So in most of the tests, we have a chemical reaction or a chemical principle to the test, although it might appear very simple. Please remember that these tests are only yes or no, and you cannot use these tests to prosecute a person. Once you know that it's adulterated, you can take it to the lab and get it analyzed, because a laboratory test is the test that will be legally accepted, not a test which you do at home. So many a times, especially in the synthetic milk, SDS, that is sodium dodecyl sulfate, or detergents are added. So if you take the milk and shake it, add an equal quantity of water and shake it vigorously. If you see a lather that doesn't go away, that shows you have SDS. Actually, when you take undiluted milk and shake it, you will also see a lather. That is because the proteins have got the emulsifying activity. But that is why we dilute the milk and then you see the lather. To see the presence of vanaspati in milk, if you take milk and you add 10 drops of hydrochloric acid and then 1 drop of sugar, after 5 minutes you check the color. A red color indicates the presence of vanaspati. So this is almost like Bowden test. Synthetic milk has got a bitter and metallic taste. It has a soapy feeling because they add SDS to it, and it turns yellow on boiling. Adulteration of spices, how do we check them? For the black pepper, if you look at the density of the papaya seeds, it is much less than that of black pepper. So you can evaluate this by taking the pepper, known pepper seeds, and adding it to a beaker containing carbon tetrachloride. So the papaya seeds, being lighter, will float on the top, whereas the black pepper seeds, being heavier, will settle to the bottom. So if you find floating seeds, you know that papaya seeds have been added. And papaya seeds are toxic because they contain a chemical called BITC, which is the butyl isothiocyanate, which is quite toxic. So how do you find whether powdered bran and sawdust is added to spices? You take a beaker of water and sprinkle this mixture, whatever is there, and you see. The powdered bran and sawdust, being much lighter than spices, will float, whereas the spice powder will settle down. In the case of chili powder, it is adulterated with brick powder, sand, and dirt. So Once again, in this, you take the chili powder and you put it into a beaker containing a mixture of chloroform and carbon tetrachloride, brick powder, and the grit will settle down at the bottom. So the chili powder being light will float, whereas the big brick powder and the sand being heavier will actually go down to the bottom. Color in chili powder, you can do it by TLC. So here you take the sample and in a beaker containing a mixture of petroleum ether and diethyl ether, you decant the solvent, concentrate and spot it on a TLC plate, and distinct spots appear for oil-soluble color on developing with the solvent. So this can be detected in the laboratory. Adulteration of turmeric powder. Generally, in turmeric powder, if we look at our regulation says, or the rule says, that the starch content should be between 40 to 60%. So generally, the vendors will buy very low grade turmeric rhizomes, and they will powder them. And since the starch will be lower, it will be less than 40%, they add starch of maize, wheat, or tapioca to add to the weight and also to meet the regulation of 40 to 60%. Now, how do you identify this in the laboratory? In a microscope, you can look at the grains and you will see that the starch grain of turmeric is different from the starch grain of maize, wheat, or tapioca. So by looking at the under the microscope, you can tell whether starch has been added. Lead chromate is a rampant adulterant of turmeric powder. So here you add 1:7 dilute sulfuric acid. So the lead chromate is converted into lead sulfate, and then you add 0.1% diphenyl carbazide. And what you get is a violet color, which indicates the presence of lead chromate. So this is a test, a qualitative test. And this qualitative test is done in the laboratory, and it is legally acceptable because the turmeric powder has to be absent in lead chromate. So a yes or no taste is more than sufficient. As I said, methanol yellow in any food and in turmeric powder, you can see that if you add acid to it, it will turn into a more violet or red color depending on the concentration of methanol yellow. And if the color persists, that is, a violet color persists, you know that methanol yellow has been added. Coffee is adulterated generally with chicory, but as per the rules, you can make a coffee chicory mixture, but if you're selling it at 100% coffee, it should contain coffee. So to detect this, you can take a measuring cylinder, fill it with water, and sprinkle it with the coffee powder sample on the surface. The coffee will float over the surface of water, but the chicory being heavier will sink to the bottom. Tea generally is adulterated. The spent tea is adulterated with synthetic colors. So one way of doing this is taking the tea, putting it between a filter paper and pressing it with the or wetting the filter paper or a wet filter paper and pressing the tea on it. If you get a color on the filter paper, that shows the tea is adulterated, because tea will only infuse the color due to the catechins the thiaflavins, and the thiarubins at high temperature. If you have got pure tea leaves in your house, when you go back, you can check it. Put it into cold water. If any color comes, is extracted, then the tea is adulterated. And then heat the same thing. If no color comes, heat those tea leaves which are put into the water, and you will find that only when the temperature reaches about 60 to 70 degrees Celsius, the color will start infusing from the tea leaves. Iron filings can be tested by using a magnet, because you know magnets will attract iron. Used tea also you sprinkle on the wet filter paper, and if you see the red spots, because they don't sell used tea as such, they generally color the used tea and sell it. Um, Other adulteration is ice cream, which is adulterated with washing powder. Washing powder is sodium carbonate. So if you take the ice cream and you add lemon juice and you see bubbles, you know washing powder is added. So what is the principle behind this? We know that when any acid is added to carbonate, or all carbonates react with any acid to liberate carbon dioxide. So the bubbles that you see are carbon dioxide. Sugar is invariably adulterated with chalk. So if you dissolve the sugar in a glass of water, if chalk is added, it will settle down. Honey, the adulteration, no, it should not be water, it should be sugar. Honey is generally adulterated with sugar. So take a cotton wick and dip it in the honey. It burns and it will give a cracking sound. Dal with methanol yellow, you add uh, hydrochloric acid. If you get a pink color, you have methanol yellow. If large amounts of methanol yellow are there, when you wash the dal, you should not get a yellow, you will get a bright yellow liquid. So go home and take your dal, wash the dal, and see whether you get a yellow color. Generally, when you wash dal, no color should be observed. Pure ghee with vanaspati. So if you take the ghee, melt the ghee, add hydrochloric acid to it, and then add a pinch of cane sugar and shake well, you will see that there is a crimson color or a crimson violet color. Common salt with white powdered salt. Again, when you put it into water, common salt will completely dissolve and any impurities will remain. So if the salt is pure, you should not have any impurities. Ajmon seeds are generally mixed with the mustard seeds. They are toxic because they contain the alkaloids, the sanguarine, and sanguarine causes dropsy. And since the mustard seeds resemble the argemone seeds, it's very difficult to separate them. And argemone seed it's a food safety hazard and causes not only beriberi but also gastrointestinal disturbances, etc. So the common toxic colors that are used in food are: methanol yellow is used in ice candy and faluda. Orange 2 is used in halwa. Rhodamine B is added to red chili powder and churan. Blue VRS is added to sweets. Auramine is added to sugar-coated somf and supari. Malachite green is added to coconut. Lead chromate is added to turmeric. And then red, yellow earth dyes are used. So these are the common toxic colors. You can, very often, rhodamine B also is used to adulterate or color sweet potato. So a very easy way of detecting rhodamine is take cotton ball, and put it into some organic solvent and just rub it across the sweet potato. If you get a pink color, it shows that it has rhodamine B. So I would advise all of you to please go to FSSA website and download these easy methods to detect. There are a large number of methods which are used to qualitatively detect the adulterants. But now you know that these and most of these qualitative methods and many more which I have not described are now being used in the mobile laboratories. That is the mobile, it is called Food Safety on Wheels, FSWs. Every state has been provided with 2 FSWs by FSSAI, and these are mobile laboratories where these simple tests can be carried out to convey to the consumer and the general public what is the level of adulteration, and public also can bring their products and get them tested. Now once it is tested there, then it has to be confirmed in the laboratory, because you cannot use that for legal purposes. Okay, now that is at the qualitative yes or no. But we can also detect adulteration, especially when the adulterant and the food look alike. How do you detect adulteration? It is very difficult to do it. But there are several molecular approaches which can be used to detect adulteration, and I will describe a few of them. So, generally, what you do is you determine the ratio between the chemical constituents which are present in the food. For a food, the ratios will generally not vary. And if it is adulterated, you will find that the ratios vary. But this is not a simple method, because here you need to use what is known as chemometrics and some very sophisticated statistics method. So the methods that are used are principal component analysis, linear discriminant analysis, hierarchical cluster analysis, soft independent modeling, partial least squares, canonical variate analysis, and artificial neural network. So very often, to use molecular approaches, we need to find a specific biomarker for a particular product, and which appears only in that product and nowhere else. It could be a chemical constituent, it could be a molecule, it could be a nucleic acid, it could be an amino acid, or it could be some morphological component of the plant. And this will help in us identifying the adulterant or telling whether the food is authentic or not. So many techniques have been used, and you will be exposed to details of the basics and the applications of almost all these techniques which are being used to detect adulterants based on principal component analysis. So we have HPLC, LC, MS, GC, GCMS, GCFTIR, atomic absorption spectroscopy, ICP, ICP-MS, isotopic ratio mass spectrometry, thermogravimetric analysis, uh, differential scanning, calorimetry, NMR, etc. So when you have these classes, you will be exposed to the basics, and you will know how they can be used for detecting and identifying compounds. So, as I said, large number of techniques are available. These include proteomics, which has been used to identify the meat type and species of the gelatin, DNA methods, which are species of variety, so you can find out even the variety of meat. So if goat meat is adulterated with chicken meat, it can be identified. If horse meat is adulterated with beef, it is identified, and that's how it was identified. Then you have stable isotope ratio analysis, which I will partially describe to you today, where it can tell you geographic origin. So it can tell you whether the kiwi fruit came from New Zealand, or the kiwi fruit came from South Korea, or the kiwi fruit came from India. Then you have immunoassay. These are ELISA. So they will detect a specific biomarker protein in the food. And we will be discussing the DNA-based methods and the protein-based methods. You could also use physical spectroscopy or microscopy, especially to find out the wheat and basmati. You can use metabolomics. That means, looking at the metabolites and then using principal component analysis, mass spectroscopy, and then you can also do chemical analysis of fruit juice, honey, nitrogen. So there is a big toolbox, large number of tools which are available to detect the adulteration and also to authenticate the food. So proteomics and DNA-based methods are very often used for the food authenticity. So I'm going to give you a few examples of things. So let us look at this. These are two fruits, elderberry and cranberry. And we have seen the other day that these are known, and especially cranberry is known for its anthocyanin content. And we know that anthocyanins are antioxidants. But cranberry is very expensive compared to elderberry. And cranberry has many more flavonoids and anthocyanins than elderberry. So generally, the cranberry juice will get adulterated with the cheaper elderberry juice. Now, how do we identify the juice? Because by looking at the pictures of cranberry and elderberry, you can identify them. But when the juice is made, it's homogeneous, so you will not be able to find out whether elderberry juice is added. So this is where we do. If we look at what I said in the toolbox, you have got proteomics or you have got metabolomics. So if you look at these, both are rich in anthocyanin. And we know that no two fruits contain the same amount of anthocyanin or the same anthocyanins. The anthocyanins are a group of compounds. So then what you can do is you can do a profiling of the anthocyanins. So what you see in the upper line is a HPLC of the anthocyanins of cranberry. So very clearly, the anthocyanin profile shows cyanidin 3 glycoside, cyanidin 3 arabinoside, peonidin, peonidin 3 glucoside, and peonidin 3. Then you can do the anthocyanin profile of cranberry. And given below is the anthocyanin profile of cranberry. And then, no, it is not the anthocyanin profile of cranberry. It is the anthocyanin profile of the juice that you are investigating. So now you compare the two chromatograms, and generally if you have in the HPLCs, we have the HPLC programs itself can do an addition or subtraction and can also tell you what the differences are. So what you see over here is this particular peak. If you see the strength of the peak is too strong relative to the other thing, because if you look at the profile of pure cranberry, you see these three anthocyanins, that is the cyanidin arabinoside, galactoside, and the peonidin. They are of equal strength. But here what we find is, we find one is higher than the other, and so. So this shows that these peaks are too strong relative to the other anthocyanins of cranberry. A second point is, there is a peak here which is not present in the cranberry anthocyanin profile. Also, this peak here is absent in the cranberry anthocyanin profile. And you can conclude that these three peaks have come from elderberry addition or any other juice. But to make these observations and to come to these conclusions, we must have authentic cranberry juice and you must have elderberry juice. And you will see that in cranberries, from region to region, there may be variation. So therefore, you have to do a cranberry profile of several regions, and using principal component analysis, get an average or get a profile which will tell us, or which can be used for cranberry. So a simple HPLC can be used to detect the adulteration of cranberry with elderberry. Okay. Now coming to our scenario, we have got, generally kesari dal is used as an adulterant because kesari dal is much cheaper than tur dal or the chana dal. It can be grown in drought conditions or in very harsh conditions. However, kesari dal causes neurotoxicity. We have seen that when we looked at anti-nutritional factors. It has got an amino acid which is beta ODAP, or that is beta oxalyl diamino propionic acid, which is a neurotoxic acid which causes neural overexcitation and paralysis, and therefore it is toxic. Also, FSSAI has banned or prohibited the presence of kesari dal in thing. So now look at these two, and I don't know how many of you can identify which is kesari dal and which is tur dal. They are almost alike. So now I will give you the answer. So on the left is kesari dal and on the right is tur dal. So all of you will be going, ooh, you know, you can't make out the difference. But you can use, this is physically, at least those of us who have seen the kesari dal and the tur dal, we will be able to identify it. But to a layman, it is very difficult. Now come to a second scenario. You have besan. So you have bought some besan powder to make some pakoras for the evening. So does it contain kesari dal or not? How do you know? By looking at it physically, you cannot tell the difference between kesari dal flour and besan flour. So the only other way is to use a biochemical or either a DNA based or a protein based or a metabolite based analysis. So this can easily be done by using HPLC. So if you look at the HPLC, what you see in lane A is pure besan flour. What you see in panel B here is the kesari dal flour. And what you see here in lane C is we have mixed one seed of the kesari dal, which is also known as grass pea, with 999 seeds of chickpea and made a flour. So here is a 0.1% adulteration, and here is a 1 is to 1000 adulteration. So what you see here is that in the chana dal, we do not have the beta ODAP peak, and in the um, adulterated at this low level, you see this peak. At higher levels, we see a higher. So many of you might be saying, it is such a small peak. How are you sure that this peak is the Kesari Dal peak? We generally do this by spiking the solution with an extract of the grass-free flour or with the standard beta ODAP, and you will see the profile will remain exactly the same, and only that peak will increase. So beta ODAP was easily detected even in the pakoda, in the bundi, in the laddu, and in dokla, because it is highly stable. It is not degraded by the ordinary cooking conditions. Another very rampant adulteration in India is that of basmati rice. So if you look at basmati, because of the price of basmati, it is generally adulterated. We have in the basmati, we have got traditional basmati. This is what is the original basmati. And we have the hybrid basmatis, which are the hybrids of the with the traditional breed. And then common adulterants where pusa, sabarmati, sharbati, which are all long grain rices, are mixed with the traditional bean, or many a times they are just mixed with this flavor component 2-acetyl 1-pyrroline, which is the basmati flavor, the major flavor component. So how do we identify this? Many of the countries abroad, including the US FDA and UK and EFSA, they have the DNA based method to identify basmati rice. So here is a very simple to explain to you the how you can identify basmati rice. So day after tomorrow, when I talk to you about the biological methods, I will explain in detail how you do PCR and RT-PCR. So here what we do is we amplify a specific part of the DNA sequence, which is very specific to basmati but absent in the other rices. So what you see here is 1 and 2. So only basmati rice will give you that band, whereas the other rices such as pusa, sharbati, and pandana's leaves are the leaves which contain this flavor component. So you see we have sharbati, we have pusa, okay, which are the adulterants. So those do not contain this. So the same thing can be done by a more advanced technique, which is called as real-time PCR, or it is known as qPCR, quantitative PCR, where you can quantify the adulteration. This endpoint PCR is a qualitative test which will tell you yes or no, whereas the real-time PCR is quantitative. So what you see here are, in this left side are all the traditional basmati varieties which amplify the gene, and you have the traditional variety which shows an absence. So therefore, using the DNA, that is as a molecular marker, you can tell basmati adulteration. And when I take the webinar on DNA based techniques, I will tell you how basmati rice is identified in the European Food Safety Authority and by US FDA. Now, another commodity we talked about earlier is the fish which are adulterated, because fish is a highly priced commodity. So here are two types of fish. One is the tuna, and those of you who eat the canned fish or who eat tuna sandwiches in Subway know the taste of tuna. And this commands a very high price, and it is subjected to regulations for catch size. You have another fish, which is the bonito, which is less in price. It looks and tastes very similar to tuna. So when you have a fish catch, it is very easy to identify the bluefin tuna from the bonito. But when I make a tuna sandwich, when we make it with a fish mince, where you mince the meat, you will not be able to tell whether it is the real tuna or it is the bonito. So here again, you can go to the DNA and look at DNA sequences which are different. So using a modification of the PCR, which is called as the RFLP, that is restriction fragment length polymorphism, one is able to identify the tuna. So this is the tuna that we're talking about, the authentic tuna. So when the DNA of the fish is extracted and it is digested with these enzymes, that is the restriction enzymes, we expect fragments of size 75 and 51, 102 plus 24, 126 and 126. So these are the different tuna varieties. So here are the other varieties from which it is adulterated. And so these, if you find the 126, you know that you have adulteration with this fish or with the this fish. Now, if you digest the DNA with rasa, if it is pure tuna, you should get 102 and 24. But if you find a 94, you know that is adulterated with either of these two. If you get a fragment which is 32, you know that it is adulterated with this or that, because what you're expecting is only two fragments of size 102 and 24 base pairs. So if you use these two digests, it's very difficult because almost all of them give you 126, except in the case of adulteration with this variety, you get 74 plus 52. So these are methodologies by which we can identify, especially in mixtures, which physically you cannot differentiate. And then look at the cheeses. So here cheese is made from different types of milk. It could be made from bovine milk and it could be made from ovine milk. Depending from which milk it is made, the price of the cheese varies. So this cheese, which is actually the ovine cheese that is from the sheep, is supposed to be a priced cheese. So generally, how much milk does the goat or the sheep give you? Not too much. So it is adulterated with bovine milk. And using the DNA-based PCR amplification, you can see that if you get a 256 base pair, you know that you have bovine milk adulteration in the cheese. So similar methods have been used to identify a large number of adulteration. But this requires skill, this requires equipment, and this requires authentic standards, what we call as certified reference materials or standard reference materials. Now coming to a technique which is commonly used, and I have included this because it is not there in the instrumentation. This is a technique called isotopic ratio mass spectrometry, or it is known as stable isotope ratio mass spectrometry. And this is the official method which is used to detect the adulteration of honey with sucrose or with sugar or high corn fructose syrup. So how does the isotope ratio mass spectrometry work? The mass spectrometry works exactly like the mass spec which will be described to you. But what is this which is the isotope ratio? Now just let's look at these. In nature, these elements, hydrogen, carbon, nitrogen, and oxygen, they exist as isotopes. So we have in the isotopes, hydrogen can exist either in as H1 or as 2H, that is deuterium, and this is a stable isotope. Carbon can exist as C12 or C13. You see, one of the isotopes is in abundance. So in the case of hydrogen, H1 is abundance. So you will find it to the extent of 99.9885%. Whereas hydrogen is very low. C13 is up to the extent of 1%. You can find it on the earth. Nitrogen, the N15 you can find, and oxygen, in addition to oxygen 16, you can find oxygen 17 and oxygen 18. So here, if you find the ratio of these two isotopes, because every food will have a certain ratio of C12 to C13. If that ratio of C12 to C13 changes, then you know something else has been added. Similarly, if the ratio of H1 to H2 changes in a product, you know that it is adulterated. So where is the application of this? So the application of this is, if you can use it in fruit juice to identify whether sweeteners have been added to fruit juice beverages or to honey. When I say sweeteners, it means if cane sugar has been added. And in juice, you can also tell whether water has been added, because the water in the fruit, that is the moisture or the water content of the fruit, has got a particular H1 to H2 ratio. And ordinary tap water or bottled drinking water has a different ratio of H1 and H2. So if you find a change in the ratio between the stable isotopes, you can say that it has been adulterated. So where did this stable isotope thing come in terms of carbon? That is the carbon 12 and carbon 13, which was first discovered. If you look at the plants, you will find that the plants, to use the carbon dioxide from the atmosphere in photosynthesis, they use different pathways. So we have plants which are known. Those of you who are botany students will know that plants use either the carbon 3 pathway, that is the C3 pathway called the Calvin cycle, where you have got the 3 carbon sugars, or plants, some plants use the C4 pathway, that means using 4 carbon sugars. Examples of these are maize, sorghum, sugarcane, and millets. And then there are plants which use the CAM pathway, example, the pineapple. Now, plants which use the C3 pathway, they have the abundance of the C13 to C12 ratio is approximately between -33 to -24%. In the C4 plants, the C13 to the C12 ratio is about 16 to 10%. So the logic over here is honey does not use, you see in honey, the bees generally do not use these plants. They use the CAM pathway. So their C12 to C13 ratio is different. Now, if sugar is added, sugar comes from sugarcane, that is the C12 thing. You see the C has this so the ratio will change. Using this logic, the isotopic ratio analysis is done, where you analyze the ratio of C13, or you measure the C13 and you measure the C12, and you do a ratio, and you can tell whether sugar has been added to honey. So to explain this to you, monocotyledonous plants such as sugar, corn, the grasses, desert plants utilize the Hatch-Slack pathway, and they typically have delta 13, C13 values ranging between -8 to -20. Other dicotyledonous plants such as the flowering plants, wheat, rice, rye, cotton employ the Calvin pathway. And you have the crassulacean acid metabolism plants, which can utilize either the C3 or the C4. So animals will incorporate the carbon through the ingestion of either the monocotyledonous plants or the dicotyledonous plant. So whichever they use in excess or they eat in excess. So actually, if you compare the European race with the US race, the US use more of maize, and so their ratios will be more towards the C4, whereas the Europeans use more of wheat, rice, and rye, not maize. So if you check the carbon 12 to carbon 13 ratio, it will be more resembling the C3 plants. So this is the technique that is used to identify added sugar or added water. So let us see how in food other than honey this is used, because in many of the juices you find these terms. We know that in the nutritional facts it is given as total sugar, which includes any form of sugar which is in the product. It could be the monosaccharide, it could be the disaccharide, it could be sucrose, it could be lactose, fructose, glucose. We find labels which say no added sugar. So when it says no added sugar, that means they are not adding any of these sugars. They are not adding the corn sweetener or corn syrup or dextrose or fructose. And free sugar is sugars which are not in the form of carbohydrate. So in the fruit industry or the juice industry, beverage industry, and many of the bakery industries, they say no added sugar. So in the case of fruit juices, if you analyze the fruit juices, you will not be able to tell whether it is added sugar or not, because what is the method that you use? In all the laboratories, we are using the refractometer reading, which we are converting into sugar. So now if you look at all these fruits, that is apple, red grape, white grape, orange, grapefruit, pomegranate, you find that there is no difference between the bottled juice as well as the freshly squeezed juice. Because what we do is we measure the sugar by putting a drop on this refractometer, and then using the conversion table we do. This does not tell us whether it is sugar from the plant or the sugar from the fruit, or it is sugar which has been added from outside, that is the exogenous sugar. But you find these labels simply squeezed and no added sugar. So how are you and me as consumers sure that they have not added any sucrose or high fructose corn syrup or any other juice? So here you can do the stable isotopic ratio mass spec analysis. So when cane sugar generally is used, you will see that you get a certain C13 by C12. If you're adding beet sugar, that also has got a certain C12 by ratio. But you can measure the ratio of cane sugar added, because cane sugar is coming from a C4 plant. But the beets are C3 plants, so it's very difficult to find the adulteration of juices containing beet sugar. But we can find out the adulteration of juices with cane sugar by doing the C12 C13 ratio. We can also find added water, because this says simply squeezed. That means there is no water added. So how do we know that? So here you do the isotopic ratio analysis of the water of hydrogen as well as oxygen, and you can detect whether water is added. However, these are very expensive techniques. The instruments are beyond the buying power of several laboratories. An isotopic ratio mass spec with all its accessories will cost more than rupees 2 crore, and you need highly competent individuals who have been well trained and who can identify the peaks and do these calculations to tell this. So although we have these high-end techniques to identify the adulteration, you also need very well trained personnel, and the equipment should be available to you. So there is a compensation here to use the simple tests which say yes or no, and you use these high-end equipment tests, use the high-end equipment to find out the adulteration. So this is just an example of one technique, but as I said, the food authenticity toolbox has got a mirage of techniques which can be used to detect the food adulteration. So by using the isotopic ratio mass spec, a group of workers actually did the mapping of the oxygen 18 and the hydrogen isotope analysis, and they plotted it. So here you have, they could tell the difference between fresh juice and juice which was made from concentrate. Because generally what you have is they make concentrates and then they dilute it. So here you have 100% juice, 100% orange juice. It's not freshly squeezed, but it is actually made from concentrate. So doing the isotope ratio analysis, you see all the fresh juice falls in this quadrant. The even fresh grape juice, you have fresh orange juice. But if you look at the concentrates fall in this quadrant. This is pineapple juice made from the concentrate, and orange juice which is made from the thing. And if you look at it, the tap water of that region, the oxygen to hydrogen isotopic ratio also falls in this region. So this clearly shows that these two juice brands are made from concentrates and water has been added, whereas these juices come from the freshly squeezed juices. So using such techniques, as I said, you can detect these high-end forms of adulteration or high-end claims by using the sophisticated equipment. Thank you. Tomorrow's webinar will be on food spoilage and food preservation.